Okay, so I want to start today by considering the following basic problem. So the problem is you're given spaces X and Y, and you want a topology on the product. Okay, so this is something that, well, we'd like for, taking products to be in operation on topological spaces. And so the question is, how do we define a topology on the product? And so we need to say when sets are open. So here's a naive guess that you might make. Well, open sets in the product should be products of open sets in the individual spaces. So open sets of X times Y are sets of the form U times V, where U is in X and V is in Y, are open. So this is a very reasonable guess, but it's wrong. So this doesn't work. It doesn't satisfy the axioms of a topology. So maybe the easiest way to see that is to consider X is Y is R. So in this case, the open sets, we're saying open sets are products of open sets, so open rectangles. And these are indeed, well, okay, so defining, okay, sorry. So the problem is that with this definition of open sets, it's not closed, open sets aren't necessarily closed under a union. So unions of open rectangles are not necessarily open rectangles. So here's another open set, another open rectangle, but the union of these is not an open rectangle. So this definition does not define a topology. Okay, but we can fix this without too much trouble. And this is where bases are a little bit useful. So remember last time that we said a collection B of open sets of X is a basis if every open set is a union of elements of B. Okay, so the main thing I want to prove here is the following lemma, which is defining a topology by a basis. So last time we talked about, we approach bases in the following way. You start with a topological space, and then you say a collection of open sets is a basis if you can write every open set as a union. But you can kind of go in a reverse direction, or maybe just a different direction, where you start with a collection of subsets that you want to be a basis for some topology, and then you define a topology where that's a basis. And this lemma says that you can do that in certain situations. So let's take X to be a set that we want to put a topology on. And let's say B is a subset of the power set. So this is a collection of subsets. That's eventually going to be the basis for some topology. So if, first of all, whenever you have two elements of B, the intersection is also in B. And if the union of all elements of script B in script B is X, so if these two things are satisfied, then B is a basis for a topology on X. So there exists a topology on X which has B as a basis. Okay, so in this way you can define a topology if you start with a collection of subsets, B satisfying these two properties here. Okay, so let's prove this. The proof is not so bad. Oh, don't go any further. Oh my gosh, sorry. Okay. Yeah, I think I can fit the proof here. The proof is short. Well, there's a natural thing to do. So let's define U in X open if U is a union of elements of B. Okay, so now what we have to do is check that this defines a topology. So there's three axioms. We want that X and the empty set are open. And indeed, well, condition 2 guarantees that X is open and the empty set is open vacuously. It's a union of no elements of B. And then, well, unions, we want unions of open sets to be open, but if you have a set that's a union of basis elements and then you union that with more basis elements, then you just get a bigger union of basis elements. So this is fine. And then the final thing is finite intersections. And this is also not so bad. So let me illustrate in the case of two intersecting two open sets. So open sets are of the form unions of basis elements, or elements of B. Technically, well, okay. So we can write it like this. So if we intersect two unions like this, then we can rewrite this as a union of intersections. So BI intersect BJ. Ugh. Over I and J. And well, by assumption 1, the intersection of this intersection is also in B. And so this is a union of elements in B. And so hence it's open. And well, okay, this was the intersection of two, but if you intersect finitely many, it's the same type of argument. Okay. Okay, so good. So now as an application, we can define a topology on the product of two spaces as follows. So application. So let's take X and Y spaces and define script B as the collection of subsets of the form U times V, where U in X is open and V in Y is open. So, well, we want this collection B to satisfy the assumptions of the lemma. So in particular, this condition one, that if we intersect two of these, then we get an element in B. So observe that if we take U1 cross V1 and intersect this with U2 cross V2, well, what do we get? Let me draw that over here. So in the case of R2, the picture is like this. We have two open rectangles and we intersect them. And the intersection here is itself an open rectangle. It's a product of open sets. So in a formula, so in general, this is U1 intersect U2 times V1 intersect V2. Okay, and so this is also of the same form of set in sets that are in script B. Okay, so from this we see that B satisfies the assumptions of the lemma. And so there's a topology on X induced from this basis, which has B as a basis. So the corresponding topology is called the product topology. On X times Y. Right, so I mean, X times Y has lots of topologies. For example, you could take the discrete topology or the indiscrete topology, but this product topology is some topology that incorporates the given topologies on X and Y. And while it has nice properties, so exercise, the projection maps Px, well, the projection map, let me just do one of them, from X times Y to X, sending a pair XY to X. This is continuous. And similarly, projecting to Y gives you a continuous map with this definition of the topology. So this, okay. So an example, let's return to this case, X is Y is R. So the product topology of the standard topologies on R has a basis the set of open rectangles. And this this is equal to the standard topology, because the standard topology also has a basis, open rectangles. And I mean, the reason is, well, the standard topology has a basis for open balls, but, well, yeah, I guess the thing to say is a set is a union of open balls if and only if it's a union of open rectangles. Essentially because any open ball, you can fit a smaller open rectangle in it, like I mentioned last time, and conversely, if you're given an open rectangle, you can fit a smaller open ball in it around any point. Okay, so open balls and open rectangles generate the same topology, and it follows that the standard topology and the product topology are the same on R squared. Yeah, so this is the product topology on R squared. Okay. All right, so hopefully now you see why bases are a useful thing to work with. Right, so now I want to switch gears. Right, so let me remind you of one of our overarching goals in the course, which is to define topological invariance. Which is to say, so let me say it this way, i.e. a property. A topological invariant is a property P, say, so that if X is topologically equivalent to Y, then X has this property P, if and only if Y has the same property. Okay, so the invariant or property is it is a property of spaces up to topological equivalence. It's preserved by topological equivalence. Okay, so we're going to be moving towards defining a new topological invariant, which is called compactness. But okay, before we get there, so let me start with a little example. So let me phrase this as a question. So which of the following is a topological invariant for subsets of R2? Okay, so the first condition is being closed. The second is being finite. And the third is being bounded. So bounded means so we say C in R2 is bounded if there exists some R so that C is contained in the ball of radius R around the origin. So set is bounded if you can fit it in some large ball. Okay, so which of these is a topological invariant? So by this, I mean, is it true that if I have X and Y topologically equivalent and they're subsets of R2 and one is closed, is it true that the other is closed? Same for finite and same for bounded. If X and Y are topologically equivalent and one is a bounded subset of R2, is the other also a bounded subset of R2? Okay, so let's answer this. So this is not invariant. Being closed is not invariant. For example, as an example, let's take X to be the graph of the function 1 over X over the positive real axis. This is topologically equivalent to Y, which is just the graph of the 0 function over the same part of the x-axis. But one of these is closed and the other is not. So here's X, and here's Y. And well, Y is not closed. Because, well, here's 0, the origin is a limit point, and it's not contained in Y. On the other hand, X is closed, which, well, you can convince yourself of. I mean, what would be a limit point not contained in X? Well, you can't find one. Any point here, there's some well, some ball that's going to be disjoint from X. Any point that's not on the graph. Okay, so this shows that being closed is not a topological invariant for subsets of R2, which is kind of strange. But okay, being finite, this is an invariant. I mean, being a subset of R2 is irrelevant for this because, and we discussed this, I think, previously in some way. Yeah, I think in the first week. I mean, a topological equivalence is a bijection in particular. So if X is finite, then Y is finite. It doesn't matter whether or not they're in subsets of R2. And finally, bounded. This is not an invariant. And well, okay, let me give you an example. Yeah, so let's take, I'm running out of room. Sorry, let me just get a little bit more room here. Let me just do a new page, sorry. So an example is to take X to be the set, well, that was Y before. And let's take Y to be the set of points on the real axis with X coordinate between 0 and 1. So here we have X is yes. So here's X, which is not bounded. It goes all the way to infinity on the positive x-axis, and y is just a finite portion of this. This is bounded. But they're topologically equivalent. So, so claim 0, 1, and the interval from 0 to infinity, these are topologically equivalent. Well, okay, I mean, for example, consider the following map. This sends x to x over 1 minus x. So this function has a graph that looks like this. It has an asymptote as you approach 1. And well, it defines a continuous bijection from the interval 0, 1 to the interval 0 to infinity. 0 goes to 0 here. And the inverse is continuous, which you can check. Okay. Okay. All right, so next, so let me tell you a surprising theorem. So here we've seen, oh, that's erased. That's not good. Okay, I'll fix that later. Sorry, I wanted to refer exactly to this. What did I have written before? I'm sorry. Okay, so we saw here that, well, being closed and being bounded are not topological invariants for subsets of R2. But the surprising fact is if you combine these, then you do get a topological invariant. So theorem, closed and bounded is a topological invariant for subsets of Rn. Okay, so this is very non-obvious, and it'll take us a couple of lectures to prove it. And the way that we will prove this, so to prove this, we'll give a topological characterization of closed and bounded. Okay, this maybe seems vague, but you'll see what it means soon enough. Okay, so that leads us to the discussion of compactness. Okay, so let's fix. Yeah, so let me start with the definition. let's fix a subset of Rn. So a few definitions here. A collection U of open sets in Rn is a cover, is an open cover of X if, well, X is contained in the union of U in script U. And moreover, if we have some subset of script U, U prime, so that X is also contained in the union of U and U prime, script U prime, then we say U prime is a subcover. And finally, we say a cover is finite, well, if it's finite, if it has finitely many elements. The elements are open sets. Okay, so U has finitely many elements. Each, yeah, okay. So an example illustrating, yeah, so let's see a few examples illustrating these definitions. So first, let's take X to be Z squared in R squared. So and let's consider script U to be the set of balls of radius 1/2 centered at some point in Z squared in the lattice. So this is an open cover. So it looks something like this. These balls, the radius 1/2, so they don't intersect one another, and each contains exactly 1 point of X. And the thing I want you to observe is that no subset, proper subset, so U prime contained but not equal to U, is an open cover. So U has no subcovers. Okay, and because, right, if you remove any one of these open sets, then you no longer cover because you don't contain the point that that open set contained. Okay, another example. Let's take X to be the interval 0, 1 in R. And let's take UN to be the open set, the interval from 1 over n to 1. So this is an open cover. So the picture UN, the UNs look like this. So U2, I guess I want to start with U2. U1 is empty. So U2 is the interval from 1/2 to 1. U3, U2. U3 is the interval from 1/3 to 1. Then we have the interval from 1/4 to 1, and so on. And altogether, these cover X. So this cover does have subcovers. So U prime set of UN. So for example, if I take all the UNs where n is greater than 100, this is a subcover. Yeah, I mean, if I just started with U100, that is this set from 1 over 100 to 1, and then, you know, then I have 1 over 101 to 1, and these also cover. Okay, so we have there are subcovers in this example, but U does not have a finite subcover. Because, I mean, if I have only finitely many of these, well, there's some biggest n, and I mean, these things are nested. And so, you know, yeah, hey, if you only have finitely many, then no single one of these covers X. You need infinitely many to cover. Okay. One more example. Now let's take X to be the closed interval from 0 to 1. And let's take UN to be -1 to 1 over n, and U0 1/2 to 2. So this is an open cover. These open sets cover. So we have this picture. So we're looking at -1 to 1 over n. So the first one, I guess, U1 is like this, and then we have U2, which goes up to 1/2, and so on. And then, well, these don't quite cover the closed interval, but if we include -1 to 2, U0, then these cover. Right, so then the thing I want to point out here is that U has a finite cover, finite subcover. Namely, U prime is U not U1. Because, well, look, I've already pictured that here. U not and U1 do cover the closed interval here. Okay. Okay, so now let me give you a theorem, which is the topological characterization of being closed and bounded. And this theorem is known as the Heine-Borel theorem. And it goes as follows. So X is a subset of Rn, then the following are equivalent. One, X is closed. Closed and bounded. And two, every open cover of X has a finite subcover. Okay, so this is, well, okay, so there's a few things to say. So one thing to observe is that this condition 2, this is a purely topological condition. It's described just in terms of open sets of X. And any property that you can describe in terms of open sets is a topological property, because a topological equivalence, well, yeah, how to say it? Yeah, I mean, topological equivalence is a function between X and Y that preserves open sets. Since open sets to open sets, preimage of open is open, it's a bijection. So any property that you can state in terms of open sets is a topological property. And so this explains, this theorem, part of the content of this theorem is that being closed and bounded is a topological property. And I guess the other thing I want to say is that this condition two, here we'll say X, this is an important property which we'll give a definition to, we say X is compact if it satisfies this property. And then let me finish with just a corollary of this theorem. Just a small corollary, although this theorem is very useful and there's lots of applications of it. So a simple thing we can deduce from the theorem is 0, 1, the open interval 0, 1, and the closed interval 0, 1 are not topologically equivalent. Because, well, this one is not closed, although it is bounded. While this one is closed and bounded. Right, so the theorem says, if you have a subset of Rn which is closed and bounded, then any other subset topologically equivalent to it must also be closed and bounded. And so from this we deduce the corollary. Okay, so this is kind of a small corollary, but it indicates the power of the theorem. I mean, how would you prove this corollary directly? I mean, it's quite difficult to show that there's no topological equivalence between these two sets. I mean, you can't do it directly. There are bijections. These sets are both, there's a bijection between them, but well, okay. Right, so this is part of the usefulness of compactness. It's a topological property, and it can be used to show that spaces are not topologically equivalent. Okay, so then the next couple of lectures are going to be focused on understanding more about compactness and proving this Heine-Borel theorem.